Hello, epidemiologists. This is the last of our EpiBiostats webcasts, and the fifth. This is before class 5. There's a homework assignment contained in this that you will need to do for the clinical epidemiology class, which I think is 2 classes away. So just pay attention to that when you see it. It's different articles for different groups, but for tomorrow, you just need to watch this and sort of understand it. So here's the goal. We're going to discuss the idea of statistical power and show an example of a power calculation. You do not need to know how to do a power calculation or know the formula for it for the exam or for the boards, but you should just understand what it is. I'm also going to present how meta-analyses are done and what they're for, and we're going to review a couple of prominent, sort of famous meta-analyses that have been used to generate screening recommendations in primary care. So what is power? I looked through all my pictures to see if I could find a picture of somebody making a muscle, and this is the closest I could come up with. This is my daughter when she was 2, almost 3, and I thought that bathing suit was very cute, and I said to her something like, "You're the best," and she made that. So power in a statistical study is having enough observations in your study to ensure the ability to find a statistically significant result if it exists. If you don't have enough observations in your study, then you can't tell whether your results are actually statistically significant and you just don't have enough patients in the study to know, or whether they were never going to be significant and you just, it was a negative finding. Having said that, there's not an absolute number for power. It depends on what you're trying to find. It depends on several parameters that have to do with your study, and we'll talk about that in a minute. So it's not like you can say, well, if you don't have at least 100 patients in the study, it doesn't have enough power. It sort of depends on what you're trying to show. So there are these things called power calculations, and there is a different one for each different statistical test, which we've already talked about in another webcast. So t-tests, chi-square tests, analysis of variance, etc., they all have their own power calculation. And the example that I'm going to show you in this webcast is about t-tests. So the power calculations include how big of a difference between the groups do you expect to find or do you want to find? And usually the question of that is like, what's a clinically significant difference? Is your p-value cutoff 0.05? Usually it is, but sometimes in particular studies you might, change it a little bit, and we talked about that in the stats lecture. What percent power do you want? Higher is always better. Usually less than 80% power is not like what you want to do. So you want usually at least 80. And if you can get 90 or 95, that's great. How many groups are you comparing? And how many observations or subjects are in each group? And that's often the part that you want to find. You want to solve the equation for that number. In some cases, in the case of t-tests and other continuous variables, the standard deviation matters. The mean and the standard deviation matters. So I'll take you through an example. Just suppose I'm teaching a med school course and the mean on the exam in 2013 was 86. And I want to see if we shake things up and change the way we teach the content in this course, whether students will do better on the exam the following year. And by better, I think like a 5-point difference in the mean would be what I would consider clinically significant. That's what I would want to see. So my question is, do I have enough students taking the exam to show whether there's a statistically significant difference in the mean? So there are these power calculators that you can look up online, and you can see the web address for this one. This is the one I always use. It's the University of British Columbia, and I use it for grants. It's a partial screenshot on the left of sort of what the power calculator looks like for t-tests. And so I'm calculating the sample size because I want to see sort of, how many students I need in my class. And it says enter a value for mu1 and mu2. That means the mean in the first group and the mean in the second group. And enter a value for sigma. That's the standard deviation. And whether it's a one-sided or two-sided test, it's usually two-sided. Enter a value for alpha. Default is 0.05. That's the p-value, so I left it there. Enter a value for desired power. Default is 80%, and so I left it that way. And then if you put in the values for the means and the standard deviation, it will tell you what the sample size should be. I should say that you can also put in an existing sample size and get it to show you how much difference you could show. So here I said mu1 is 86. That was the mean last year. Mu2 is 91. That's what I hope the difference will be. Sigma, the standard deviation, is 6. I had totally made these numbers up, but just for the purposes of this example. And I left 0.05 and 80% because we usually use those numbers. And so I put all those in, and I'm going to press the calculate button, and in the next slide you'll see what we get. So we need to have 23 students in each group, meaning 23 students in the 2013 group and 23 students in the next year's group to show that there's a statistically significant difference. That's not that many students for what we're trying to show. So, you know, the other thing you could do is to say, well, I have 160 whatever students in my class. Let me plug those in and see, maybe I'd be able to show a statistically significant difference of a smaller amount, like 86 to 88, or maybe I'd be able to show it with 90% power. So you could put different numbers into this and kind of mess around with it a little bit and see what your numbers are like. Most people use these power calculators to figure out how many subjects they need to enroll in their study. But in some studies, when you know how many subjects you have, you can play with it a little bit and say, well, what's the smallest difference that we have power to find? So this is how we use them. We figure out how many subjects to be enrolled in a study, and I use this all the time for writing grants and figuring out sort of how big the study needs to be. Or you can plug in the numbers you already have and see how big of a difference you can find. If I was really doing a research project about this class, which I'm not, I would say, well, gee, there's like 165 or so students in the class, and that's just the number I have. So let's plug that in and see whether I have enough sensitivity or power to find a 2-point difference in the mean of the exam. So there are equations for this that you can look up in the same way that you can look up the equation for the t-test and everything, but people always use computer programs to do this. Even the biostatisticians that I work with don't remember the power calculation, they just use a program. The important thing about power calculators is you have to understand the assumptions that you're putting in. You have to understand that what you're asking this is, do we have enough power to find a 5-point difference in the mean? Do we think that's an important difference? Are we okay with 80% power? Do we want it to be higher? Those are all questions you need to know. And most importantly, you need to know what kind of statistical test you are doing. So one spin-off from thinking about power is the question of what is a meta-analysis. This is a type of study that we have not talked about yet. A meta-analysis is not a new study in which new subjects are recruited and information is gathered from them. It is a look at several studies that were already conducted. And meta-analysis is a statistical technique that's used to pool the results of several studies. It's not actually simply averaging the results of each study. For example, if you have 7 studies about mammography showing that the odds ratio of finding a breast cancer if you do a mammogram or whatever is different, slightly different in each study, and you just average the 7. It's not that simple. It's actually taking the results of each individual enrolled in each study. So if you have 7 studies and one of them has 100 patients and one of them has 1,000 patients, obviously the one with 1,000 patients counts more. And so you're basically taking all of the subjects that were in all of those studies and plunking them into one statistical analysis together as though they had all been analyzed at the same time. This allows you more power, because more observations is always more power, to look at results that are subtle, like where the odds ratio differences are pretty small, or results that are maybe controversial, where some of the studies found benefit and some didn't. And especially in cases where public health interventions are involved, especially if they cost money, people like to use meta-analyses to say, looking back over the last 10 years of, say, all the mammography studies, did they actually show a benefit of screening for breast cancer? Because if they didn't show a benefit, then we're not going to cover it anymore with insurance. So how are meta-analyses done? When you read your meta-analyses, the method section will be fairly long. There's a couple of important steps that are always done the same way that you just need to understand. So I'm going to go through them here. The first one is to find all of the relevant trials to include in your meta-analysis. And this seems simple. You just go to PubMed and search them all. There has to be a systematic way that you employ to find them, to make sure that you have found them all. One issue is, do you want to include just published studies or also clinical trials that had like negative findings and weren't published? So people often deal with that. There has to be a good search strategy so you're sure that you don't miss any. Sometimes people will cut off and say, well, we didn't include anything from before 1980 or whatever. So there's rules about how the relevant trials were found. The next step is, once you have the trials that you're going to include, you look at the subjects in all of the relevant trials and decide whether you want to include all of those subjects in your final analysis. Sometimes the people doing the meta-analysis will have issues with, say, the way one site of one trial's subjects were randomized or dealt with, and they'll want to drop them out of the final analysis. A good example of this is several years ago there was a Cochrane review done on mammography. The Cochrane reviews are these it's a famous body of researchers that review data, and they're usually in Europe or Scandinavia, and they render opinions on questions that we think we've already sort of found the answer to, but they look more critically at the trials. The Cochrane review was to deal with the question of, should we even do mammograms at all? And they had issues with the way some of the subjects in some of the original mammography trials were randomized. And so what they decided to do was just exclude any subjects that they had any doubts about. And the conclusion of their study was that we shouldn't do mammograms at all because the findings were sort of neutral. So I was asked to write sort of a commentary piece on their meta-analysis, and I included that in the homework in the reading for today. It's very short, but you can read through it and sort of see what you think. But what I wrote hopefully sort of explains this issue a little better as well. And then once you've come up with your final number of subjects, you actually just run the analysis again using statistics, which you know how to do now, and decide sort of what the aggregate result is. And you'll see some of those coming up in some charts. So there are several sort of important landmark meta-analyses that have informed the workings of the U.S. Preventive Services Task Force, which is a task force body convened via the government from Health and Human Services, with many, many researchers and doctors on it from all over the country. And they review the results of these meta-analyses, and then they make recommendations about what diseases we screen for and in what age groups. So they are the people that have come up with the recommendations, say, about how often we do pap smears and in what age groups, how often we recommend mammograms and in what age groups. And when you go to the doctor and they say you should have a pap smear or you should have your cholesterol checked, they're probably telling you the recommendations according to the U.S. Preventive Services Task Force. There are other bodies, for example, specialty-based bodies like American College of Obstetrics and Gynecology has a pap smear recommendation too, which is very similar to the USPSTF. Sometimes there are differences if a professional body recommends screening versus USPSTF. And I think they look at the data through different lenses. So sometimes a professional body like the American Cancer Society or ACOG, their goal is to eradicate cancer. And so sometimes they recommend, for example, doing cancer screening earlier or more often than USPSTF does, because USPSTF looks solely at the data in the meta-analysis, and they make sort of a very rational decision, like what's the greatest good for the greatest number. And that controversy, that sort of tension between, say, the American Cancer Society recommendation and the USPSTF recommendation is what that controversy is about for mammograms between age 40 and 50, which if you haven't heard that controversy, I'm happy to discuss it more in class. But it was popular a couple of years ago. There was a lot written in the press about this. So this is the famous breast cancer meta-analysis that was done in 2009. And you can see it says this is an update of evidence since 2002. So this is what the USPSTF used for its 2009 recommendation. All meta-analyses will have an abstract, like the one that you see, and you can pause this and just read it. It's fairly clear about sort of how the data were extracted, studies selected, etc. And then, this is a sign. You can find it on Blackboard, so you can read through the article as well. The other thing I wanted to show you is this what we call this box plot thing, the graph with the squares with the lines through them that you see on the right. All meta-analyses have a table like this that shows you the final result. And unfortunately, the studies are all listed on the left-hand side. So the studies will say like Smith et al. 1983, Wilkinson et al. 2001, etc. And I couldn't get my camera screen big enough to include the names of the studies as well. But each one of those lines with the little square corresponds to a study. And the size of the square corresponds to the number of subjects that were in that study. So you can see some of them were bigger than others. Now the 1 is a neutral result. And as you can see at the bottom, if it's to the left of the one, then it favors screening. So many of the studies favored screening. Some were fairly neutral, but a lot of them had 95% confidence intervals, which crossed 1. The 95% confidence interval is represented by the line that goes through the box. And then the diamond at the bottom is the aggregate result. When you pull all the results of all the studies, that's kind of the final word. And as you can see, it slightly favors screening, but it's not a slam dunk. So, I mean, it doesn't touch 1, but it's not much to the left of 1. You'll see in comparison with the pap smear one, which we'll see a little bit later, that one is very far to the left of the 1. So the homework for groups 1 through 6 is to go to the USPSTF website, just Google it and you'll find it, and look up the current recommendations regarding screening for breast cancer. Do they concur with what was found in this meta-analysis? And the people who are in these groups, read the breast cancer meta-analysis that I just showed you sort of excerpts from. Read it start to finish. It's on the Blackboard website before class 7. You guys in these groups will do an exercise in class that has to do with this breast cancer screening meta-analysis. People who are in other groups, don't worry, I have something for you to do too. So here's another meta-analysis, a famous one, on screening for prostate cancer. This is actually fairly controversial whether it's worth doing or not. The screening tool that we have for prostate cancer is a blood test called the PSA, the prostate-specific antigen, and we order it a lot in men over 50, but it's not clear that ordering it actually reduces mortality from prostate cancer, and that's what this meta-analysis will show. So again, on the left you have the abstract. You can pause this and look through it if you want to. On the right, I'm showing you a table that you also will often see in a meta-analysis, which is like a flow chart where they show you how they found studies and then how they sort of went through them and decided which ones to include and exclude. And so you can just kind of look at that for a minute as well. And when you read the article, those of you who are assigned this article, you can look at that in more detail. So there are 2 of these graphs, like the ones you saw in the breast cancer article. The one on the left looks at the effect of screening on all-cause mortality and also death from prostate cancer. And you can see that most of the studies were fairly neutral on this. I should also mention that the size of the box has to do with the number of participants in the trial. So like the top study had the most men in it, the other ones had fewer numbers of men. You can see that in almost all cases the horizontal lines cross the vertical line. The diamond at the bottom is very, very subtly in favor of screening, but it touches the 1. So it's not clear that it actually helps. That screening actually reduces all-cause mortality and or death from prostate cancer. The second one, they actually looked at a different outcome. They looked at effects of screening on prostate cancer stage at diagnosis. In other words, do you find prostate cancer earlier if you screen for it? And you can see that they looked at stage 1, stage 2, and stages 3 and 4. And they again looked at all these different studies. You can see the results here. And it does not look like the total at the very bottom made any difference. Again, it's very subtly on the control side of 1. So to me, this is a less definitive result in the meta-analysis than the mammography one was. And indeed, you'll see when you look at the U.S. Preventive Services Task Force website that it's a little bit unclear what we do about screening. So if you are in groups 7 through 11, I want you to go to the USPSTF website and read the current screening recommendations on prostate cancer. And I'm very sorry. I'm sorriest for the people in these groups because prostate cancer is a difficult one. And many physicians in primary care are kind of frustrated with these recommendations. So see whether you agree or disagree based on what this meta-analysis found. And the people in these groups, I want you to read this meta-analysis before class 7. You'll do an in-class activity based on this. This is the last one I'm going to show you. It's on pap smears. And pap smears, of these 3, between mammography, prostate cancer screening, and pap smears, this is like pretty clearly a win. And so the meta-analysis will look very definitive. So you see some of the abstract. You see, again, one of these flowcharts where they found a bunch of citations and they excluded a whole bunch, and then they looked at, eligibility and how they sort of excluded things, and they wound up with, it looks like 24 studies that they included in the systematic review. Here is your chart for exposure to cytology, which means doing a pap smear. You can see that almost all of the studies that were done favored pap smears, although 2 of them had horizontal lines that crossed 1, meaning they were not statistically significant. And the diamond at the bottom is very clearly in favor of doing pap smears. So the homework for the last couple of groups is to, again, go to the USPSTF website, read the current screening recommendations regarding cervical cancer, and see whether they fit with what you found in this meta-analysis, and then read the meta-analysis before Class 7. So different people will be reading different meta-analyses. You're welcome to read all 3, but I at least want you to read the one that's assigned for your group, because you will do a small group activity on it in class for Class 7. And if you have questions, you can reach me. I think you should know where to reach me by now.